Good afternoon, students. Let me start the class now. As I told in the morning's class, I thought I will share some of the information about the radio spectrum's allocation. Even though this is not in our syllabus, I thought it is a good idea to show it to you so that you will get an idea about how different applications of wireless communication are existing and how the spectrum is being utilized. I will not take much time in these slides. I will go quickly. This is only for giving you an information. So our application starts directly from 125 kilohertz itself. 125 to 134 kilohertz is used for RFID applications. And amplitude modulation radio broadcasting 535 kilohertz to 1.605 megahertz. Shortwave radio is from 5.95 megahertz till 26.1 megahertz. Now it is almost obsolete. This citizens band radio, or it is also called as ham radio, its range is 26.96 megahertz till 27.41 megahertz. Cordless phones used to use 40 megahertz to 50 megahertz, and now they also have become almost obsolete. The analog television channels 2 to 6 used 54 megahertz till 88 megahertz, whereas FM radio is using 88 megahertz till 108 megahertz. This is even now prevalent. Actually, now it is more popular compared to the olden days. Now, aeronautics is using 108 megahertz till 144 megahertz. Maritime or ship communication. Ship has to communicate from the shore to the ship. So that is around 146 megahertz till 170 megahertz. And the television channels, again analog channels from 7 to 13 is 174 to 216. There are frequencies allocated for wildlife tracking. You might have heard about the King Cobra project at Agumbe or the project of white tigers in Bengal, where even the wildlife is being tracked, for which a frequency is allocated from 215 to 220 megahertz. Radio keyless systems, keyless entry systems, or an example is tire pressure monitoring systems. As soon as a car enters into a garage, as soon as the car is entering, its tire pressure can be sensed. Even when the car is entering into a petrol pump also, its tire pressure can be sensed, for which 315 megahertz till 433 megahertz is allocated. The digital television channels 14 till 70 are using 470 megahertz to 806 megahertz. Then comes the cellular applications such as Pacific Digital Cellular 810 to 960 megahertz in Japan. CDMA is 824 to 894 megahertz. GSM is 890 to 960 megahertz. And then air traffic control radar is using 960 megahertz till 1.215 gigahertz. You can now see that from kilohertz we moved to megahertz. Now from megahertz we are moving to gigahertz. GPS is 1.227 gigahertz till 1.575 gigahertz. Satellite phones, especially the Global Star, was using 1.61 gigahertz till 1.625 gigahertz. And again in the GSM, there used to be a second band and a third band, DCS and PCS. They used to use 1.71 gigahertz to 1.88 and 1.85 gigahertz to 1.99 gigahertz. The emergence of 3G happened with the UMTS, that is using 1.92 gigahertz till 2.17 gigahertz. And the deep space radio is 2.29 gigahertz till 2.3 gigahertz. ISM band is using 2.4 gigahertz till 2.4835 gigahertz, which itself is used by Bluetooth as well. Microwave ovens, their oscillator is oscillating at 2.45 gigahertz. Even though it is not a spectrum allocation, because that frequency is under usage, I thought let me put it here. The allocation of bands are there for the satellite communication right from 1.7 gigahertz till 300 gigahertz. There are different bands available: L, S, C, J, X, Q, K, K, R, V, W, and then we have millimeter wave bands from 110 gigahertz till 300 gigahertz. There are newer names given to all these bands. Of course, this may not be of much interest to you, so I will not go deeper into this. You need not remember all these things. The further allocations are for the radio altimeters 4.2 to 4.4 gigahertz. Wireless LAN belonging to 802.11a is 5.15 to 5.825 gigahertz. Police radar has got 3 bands there, X, K and Ka bands. DTH services using 11.7 to 14.5 gigahertz. And automotive radar is 24 gigahertz. Again, one more band is there, 76 to 77 gigahertz. 4G wireless is 59 to 66 gigahertz, which is already emerging into the field now. E-band or the new ultra high speed data communication band is using 76 gigahertz, 81 to 86 gigahertz and 92 to 95 gigahertz. So I showed you all these slides just for you to get a rough idea about right from kilohertz till gigahertz. We have not left any band anywhere empty, which means even though we call it as a free space, the space is no more free. And at the same time, even though we call it as empty space, the space is no more empty also. Space is busy propagating radio waves and space is filled with all types of radio frequencies, right from kilohertz till gigahertz. This I wanted to show you just for the sake of information. Now let me stop sharing this and let me start the regular class. Okay, we were discussing about the stochastic process in the morning and we were discussing how to model it using a process called Markov process or Markov process. And I have been telling the characteristics of this particular Markov process. The first characteristics was based on the transition probability when the system moves from one state to another state. Now the second characteristic of the Markov process is the source emits a symbol during each transition. Means when the state changes from the first state to the second state, during the transition, that is when the source is emitting a symbol, which means the states are actually equivalent to emission of symbols only. Otherwise, the source will remain in the first state itself. Only when the source starts emitting symbols, we can say that it is going from the first state to second state to third state to fourth state, that way it can go on. So the second characteristic of the Markov modeling is that the source emits a symbol during each transition. That means from one state to next state. If S1, S2, so on till Sm are the symbols of the alphabet, and if capital X1, capital X2, so on, capital Xk, so on it goes on. If these are the sequences, each sequence contains a set of symbols. That means X1 can contain S1 till Sm, X2 also contain S1 till Sm. I have been giving you the examples earlier, varied examples of usage of English language itself. A sentence can contain all the alphabets of English language. Even a paragraph can contain all the alphabets of an English language. Or a page in the book can contain all the alphabets of English language. So they are called as sequences here. And S1, S2, Sm, they are the symbols of the alphabet as such. Then the symbol SQ is emitted with the conditional probability that capital P of Xk, where Xk is a sequence, which is SQ in relationship with X1, X2 until Xk minus 1, which is nothing but probability of Xk equivalent with SQ bar Sk, where Sk is a discrete random variable representing the state of the system at the beginning of the kth interval. Don't get afraid or frightened by all these expressions. This is a general mathematical way of representation. So here the symbol SQ is emitted with the conditional probability. we will have symbols from S1 till SM. In between, we have a symbol called SQ. Now we have to find out the probability of the emission of the symbol SQ. Now that is called as a conditional probability, which means there are now these many symbols and all symbols are statistically dependent. When all symbols are statistically dependent, the probability of this SQ being emitted is xk equivalent to SQ bar x1 till xk minus 1, or it equals capital P of xk equal to SQ bar capital Sk, where this Sk is a discrete random variable. You will have to recall the learning of your statistics. Now this is a discrete random variable. Why we call it as random variable? Because we are dealing with stochastic processes. And why do we call it as discrete? Because we are dealing with discrete information sources. All our information sources will emit symbols one after the other. That is why they are discrete. And why it is random? Because out of the 26 alphabets, randomly any alphabet may be emitted. So it is basically a stochastic process. Speaking itself is a stochastic process. Writing, typing, everything itself is a stochastic process as such. Because all these symbols are statistically dependent with each other, and all these symbols can be utilized for information transfer, where the complete typing of a text itself is a stochastic. That is when this capital Sk is a discrete random variable representing the state of the system at the beginning of the kth interval. Okay. Now, even though this equation seems strange, we are going to use these concepts in the solving of the exercises. There you will understand better. That is the second characteristic of the Markov process. Now, the third characteristic of the Markov process is the transitions of the system can be represented in terms of its state probability. Remember, each state will have its own probability. In the morning, I was giving an example that I staying at home, I come into 11th cross, I come into Vinayaka circle, that way. It is a daily happening in my case. Okay. So, each state has got its own probability. Me staying at home, me coming to 11th cross, me coming to Vinayaka circle, all that, its probability can be computed by my daily activity. Now that is called state probability. But I move from one state to another state. There is a transition happening. The transition of the system can be represented in terms of the state probability itself. It is as if Pj of k plus 1 is summation of I equals to n of Pi of k into Pij, where Pi of k is the probability of the system in the ith state at the beginning of the kth symbol interval, which means during transition itself the symbols are being emitted. Now the system can be in any particular state. When it moves to the next state, it is emitting the symbols. Now when it is emitting the symbols, the probability of it going into next state, the probability of the system going into next state is the summation of its previous probabilities from I equals 1 to n. All the previous probabilities, Pi of k into Pij. You are already familiar with this Pij, that is nothing but the transition probability. Now, I moving to Windsor Manor Bridge, if at all that probability has to be considered, then all my previous state probabilities have to be considered. From whom I come into 11th cross, I come into Vinayaka circle, I come into the underpass, all that probabilities have to be considered, because only then I am moving to Windsor Manor Bridge. Now, between my home and my college, if there are 200 such states, let us say when I reach college, all the previous 199 state probabilities have to be considered, because I come to college only by passing through all those junctions or the traffic signals. They are all statistically dependent. They are all related. Same way in the case of our information source, the transitions of the system can be represented in terms of its step probability in this manner, where P of k is the probability of the system in the ith state at the beginning of the kth symbol interval. Now here, small p represents individual probability, whereas capital P represents joint probability. This you have to remember. Even in the exercises, we will have notation of small p and notation of capital P. Till now, whatever exercises we worked out, we always used small p only. We did not use capital P. But from now on, as we deal with the statistically dependent symbols, as we deal with the Markov processes or Markov modeling, we will start using capital P as well, which is nothing but the joint probability. The discrete stationary Markov sources are represented in a graphical form with states as nodes and the transition as arcs. Now, how do you represent these information sources? We are emitting symbols discretely. We have to go for a graphical representation where we will represent each state as a node and we will represent each transition as an arc, because symbols get emitted only during transitions and that can be visualized in the arcs. Let us have an example now. Consider a source emitting one of the three symbols A, B and C as shown. Now it is going to emit three symbols. It is going to emit A, or it is going to emit B, or it is going to emit C. Now the system can have three states based on these symbols only. Let us say system is in state 1. Then the system moves on to state 2. Then the system moves on to state 3. Let us imagine the system having only these three states. Okay. Now in each state, there is a transition and the system is going to emit symbols. Let us say the source is emitting a symbol A remaining in state 1. Now let us have the probability half. For the source emitting A being in state 1, we can have the probability half, because it can equally emit B also, equally emit C also. What we can do is, let us allocate 1/4 for B and 1/4 for C. So the net probability is unity. Just understand this. System remaining in state 1 can emit three symbols A, B and C. In state 1, it emitting symbol A, let it be half. And in state 1, it is emitting C and B, let it be 1/4. This is a typical example. Now let us say the system is in state 2, or the source is in state 2. Now the source emitting symbol C, let it be half. Source emitting A or B, let it be 1/4. Lastly, the source is in state 3. It emitting symbol B, let it be half. It emitting A and C, let it be 1/4. Now these are individual probabilities of A, B and C remaining in each state. Now the source can go from state 1 to state 2. Source can go from state 1 to state 3. That is also possible. Now when the source goes from state 1 to state 2, it has to emit symbol B, because in state 3 we have considered symbol B. In state 2 we have considered symbol C. This is just a typical example. It can always change based on our own requirements. So now you understand this particular picture. We are representing an information source as a Markov model or a Markov model or a Markov process, and we are representing this process by means of a graphical diagram. In the graphical diagram, we are indicating three states 1, 2, 3, and each state can emit three symbols A, B, C, and for each of the emission of the symbols, we are allocating the probabilities. Okay. Just remember this diagram. Based on this diagram, we are going to solve an exercise. Now, let us say the source in state 1 emits A, then emits C. If it is emitting A, then the probability is half. It is emitting C, then it is going to state 2 and the probability is 1/4. As if I stay at home and I start my bike, I forget that I am not carrying the mask, I go back home. Imagine that way. Imagine that probability is half. And from home, I come all the way to 11th cross. Imagine that probability is 1/4. Now, when I come up to 11th cross, again I forget that I have, again I remember that I have forgotten to wear the mask. I go back home. Let the probability 1/4. I am giving a very crude example, but just visualize it that way only. Because in real life, we are going to deal with real information sources. So, I am giving an example of myself. So, me going back to home is probability half. Me coming to 11th cross is probability 1/4. From 11th cross, me going back to home is also probability 1/4. Now, what may be the state B? Instead of 11th cross, I may go to 13th cross. Imagine that way. Imagine that way. If I go to 13th cross, that is state B. Again from 13th cross, I come back to my home, 12th cross, that is again emitting symbol A with the probability 1/4. This way we can visualize that the information source is having 3 states, and in each transition it is going to emit a particular symbol, and each symbol will have its probability. Now we have to deal with the transition probability, we will have to deal with the joint probability. Okay, when we have to consider sequences now, if we consider A and C, C being emitted after A, now they are statistically dependent. Just recall, we used to calculate entropy just by the summation of the individual probabilities. But now the things are different. When we calculated entropy earlier, we had assumed that the symbols are statistically independent. But in real life, the symbols are statistically independent. So the calculation of entropy for these sources is going to change now, because we have to compute the joint probabilities. That is the idea of Markov processes. So now let me proceed. It is evident from the graph that the source has 3 states, A, B, C. Now let us assume that all the states are to be of equal probability. The probability of the states is given by P1 equals P2 equals P3 equals 1/3. See, capital P is used here. This is the probability of the state. Now in my case, me staying at home and me coming to 11th cross, me going to 13th cross are all equally probable. We have to assume that way. For the time being, we have to assume that all the states have equal probability. Otherwise, things are going to become much more complicated. As I told you, it is not possible to completely model a stochastic process as such, because there are too many parameters there. For the sake of simplicity, let us assume that all these 3 states have equal probability. If all these 3 states have equal probability, then naturally probability of A equals probability of 1 equals probability of 2 equals probability of 3. Because this 1, 2 and 3 are nothing but the states of the information source or the system. So P1 equals P2 equals P3 equals 1/3, because we have only 3 states. Now, let the probability of the system emitting the same symbol be half, because that is more probable, and that emitting different symbol be 1/4. In state 1, it is emitting A, that is more probable, and it is emitting B and C is less probable, let it be that way. Then PAA is half and PAB and PAC is 1/4. From A, it is emitting another A is half. From A, it is emitting B is 1/4. From A, it is emitting C is 1/4 and so on. It is as shown in the graph. Now, the state transitions and the symbol emissions can be represented in a better way by means of a tree diagram now. We can write a tree diagram for each emission of the symbol from each state. Let us start with state 1. Okay, let us start with state 1. Now, you can see state 1. In state 1, the probability of the state itself is 1/3. Now, it emitting A is half. It emitting C is 1/4. It emitting B is 1/4. After it emits A, it is again in the state 1 itself. Again it is emitting A is half. Again it is emitting C is 1/4. Again it is emitting B is 1/4. So we can say after it emits A for the second time, it is again in the state 1 only, that is AA. I leave home, I go back home, again I go back home twice, forgetting something again and again. Now that can be 1/3 into half. That is sequence AA. Now this becomes a joint probability. This half itself is a transition probability and totally it is going to become a joint probability because they are statistically dependent. Now in this way, for each sequence, we can compute the joint probability for AA, AC, AB, CA, CC, CB, BA, BC, BB. Just imagine for an information source having only 3 states, emitting only 3 symbols, we are writing this tree diagram so as to have more clarity, and we can have such another 2 tree diagrams. Why? We have written only considering state 1. Similarly, we can write one more tree diagram for state 2, one more tree diagram for state 3. Actually, it is written. I am going to show you later on. So there can be a sequence of AA, AC, AB, CA, CC, CB, BA, BC, BB, because from state 1 C is emitted and from state 2 A is emitted, so that becomes CA. Similarly, if it is state 2 here, this can be B here. Okay, I will show you that. If it is state 2, now it is again state probability is 1/3. Now from state 2, it is emitting A or emitting C, emitting B. In state 2, it is emitting C is probability half. Other 2 are 1/4. Now again it will go into one of these 3 states. Again it will go on like this. Again, remember, we are considering only sequence containing 2 symbols. We are calculating or computing the joint probability for the sequence containing only 2 symbols. Again, AA, AC, AB, CA, CC, CB, BA, BC, BB. That way. Now, last one is this information source is in state 3. And then it is emitting A, C, B. Again, state 1, 2, 3. Again, it is emitting A, C, B. Again, A, C, A, B, C, A, C, 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 B. BA, BC, BB. It goes on this way. Now for the complete information source, we have 3 tree diagrams, and in this complete information source, we are considering sequence containing 2 symbols, and there are 3 such sequences. For example, AA is here also. In the very first diagram, AA is there. AA is there in the second diagram also. AA is there in the third diagram also. Sequence AA gets emitted when the source moves from state 3 to state 1 to state 1. The same AA gets emitted when the source moves from state 2 to state 1 to state 1. Similarly, the same sequence is emitted when the source moves from state 1 to state 1 to state 1. Just look at this diagram again. A is possible here, A is possible here. Same way, A is possible here, and again A is possible here. And again from state 2, A is possible here, then A is possible here. So there are these many ways of A being emitted. There are 3 ways of A being emitted. That is what is indicated here. Similarly, it is there for ACAB, CAC, CCB, BABC, BB. Okay. Now these are the 3 tree diagrams. This tree diagram can be utilized to obtain the probabilities of generating different symbol sequences of length 2. Why we have considered only length 2? If we consider length 3, then this page is not enough for me to draw the diagram itself. Manual computation will become much more difficult. Anyhow, nowadays we don't have any manual computation at all. This manual computation is done only for the sake of understanding and clarity. Otherwise, all this job can be easily given to the computer itself. A program can be written in C language or in MATLAB for all these computations, and all these repetitive competitive work can be done by the computer itself. But for the sake of understanding this concept, we are dealing with the sequences having only length 2. Okay. So this tree diagram can be utilized to obtain the probabilities of generating different symbol sequences of length 2, such as AA, AC, AB, and so on. Let us consider the 2 symbol sequence AB. Let us consider only one out of this. We have 9. Out of 9, we will consider only the symbol sequence AB, which can be generated by means of these following transitions. It is state 1 to state 1 to state 3. State 1 to state 1 to state 3. See, state 1 to state 1 to state 3, that is AB. So it is 1/3, 1/3 into half into 1/4. 1/3 into 1/2 into 1/4. That is going to be the joint probability there. State 1 to state 1 to state 3 is AB. This is 1. One more is again state 2 to state 1 to state 3. That is also there. Again here it is 1/3 into 1/4 into 1/4. Lastly, state 3 to state 1 to state 3. That is also AB. That is again 1/3 into 1/4 into 1/4. So in these 3 ways, the sequence AB can be emitted from the information source. That is what is indicated here as the transitions. State 1 to state 1 to state 3, state 2 to state 1 to state 3, state 3 to state 1 to state 3. That is A and B. Now let us calculate its probability of occurrence. It is capital P because it is joint probability now. Probability of occurrence of AB is equivalent to probability of state 1 is 1, state 2 is 1, state 3 is 3. That is 1, 1, 3. Or it can be S1 equals 2, S2 equals 1, S3 equals 3. That is 2, 1, 3. Or probability of S1 equals 3, S2 equals 1, S3 equals 3. That is 3, 1, 3. There are 3 ways in which AB will be emitted. Now this is what I was mentioning at as a discrete random variable. Okay. When I was discussing the second characteristic of the Markov source, I was mentioning this only as the discrete random variable. Let us calculate now. As the 3 paths are disjoint, all these 3 paths are disjoint because they are not related. This path of 1, 1, 3 is disjoint from the path 2, 1, 3 and disjoint from the path 3, 1, 3. That you can see in this diagram itself. In this diagram itself. 1, 1, 3 and 2 and 1 and 3 and 3 and 1 and 3. All these are disjoint paths. So as these paths are disjoint, let me come back. As the 3 paths are disjoint, the probability of A and B is the probability of 1 to 1 to 3 plus probability of 2 to 1 to 3 plus probability of 3 to 1 to 3. When they are disjoint, the probabilities can be added. That means these paths are not dependent on each other. Symbols are dependent on each other. Symbol emissions are dependent on each other. But the paths are disjoint. For example, me going from 12th cross to 11th cross, me going from 12th cross to 13th cross, that is dependent on me. But as such, 11th cross remains 11th cross, 13th cross remains 13th cross there itself. They are disjoint. People going on those roads, they can go to any particular roads based on their choice. But as such, those roads or crosses are disjoint. So as these paths are disjoint, the probability of occurrence of A and B, or to be precise, the probability of occurrence of B after A, is the sum of these 3 probabilities which are indicated in the tree diagrams. But now the state probabilities are joint probabilities. Within the state, it is joint probabilities. Okay. So the transition of 1 to 1 to 3 is always a joint probability. It has to be multiplied. If it is a disjoint probability, it has to be added. Remember this. If they are statistically independent, probability has to be added. If they are statistically dependent, probability has to be multiplied. You will have to recall whatever you have learned when you learnt probability and statistics. The events which are independent of each other, their probabilities are going to be added. The events which are dependent on each other, their probabilities are going to be multiplied. If you remember this, that is enough. Or you simply remember this way. Which way? Disjoint means addition and joint means multiplication. You remember this way. Disjoint means addition. Here the 3 paths are disjoint. So it is the addition of all those probabilities. But within each transition, it is statistically dependent because it is symbol emission now. So there it is joint probability. So in such a case, it has to be multiplied. Remember this way. Disjoint means addition, joint means multiplication. Remember it that way. So now, total probability of A and B sequence occurring is equivalent to 1/3 into 1/2 into 1/4, as I have been mentioning earlier, plus 1/3 into 1/4 into 1/4, plus 1/3 into 1/4 into 1/4. We can summarize this. 1/24 plus 1/48 plus 1/48, it is 1/12. This is a joint probability. Remember this. It is a summation of the joint probabilities. Remember this. So P of AB is 1/12. Similarly, we can find out P of AA is 1/6. P of AC is 1/12. Similarly, we can get P of CA equals P of CB equals P of BA equals P of BC equals 1/12. And we can also compute P of CC equals P of BB equals 1/6. So, A occurring after A is 1/6, C occurring after C and B occurring after B is also 1/6. Why? The probability of A occurring in state 1 is taken as half. Similarly, the probability of B occurring in state 3 is taken as half. And the probability of C occurring in state 2 is taken as half. That is how we get different results here. So this is how we can find out the probabilities of occurrence of a sequence. When we find out the probabilities of occurrence of a sequence, later on we can compute entropy for the given sequence. That is the idea here. Once we find out entropy, we can gradually find out the information rate for a given information source. That is the idea here. Okay, there's a note here now. Let me take a small break for sipping water. The note is, here we have assumed that the Markov property is utilized, which means that the residual influence lasts only for a duration of one symbol. This is important. We have assumed that the residual influence lasts only for a duration of one symbol. That means from one state to next state, that relationship we have considered. The third one we have not considered. If we consider all that, then our computation is much more complicated. That I have been telling you repeatedly. So, we think that the residual influence lasts only for one symbol because in each state, in the transition, during the transition, the source is going to emit a symbol. What is meant by the residual influence? There is a statistical dependency. That statistical dependency is lasting only for that particular duration. This is what is meaning. Now, from the 12th cross, me moving to 13th cross or me moving to 11th cross, that residual influence lasts only in between those two roads. That is what is the meaning here. Later on, I may go to 14th cross or I may go to 9th cross. Now that will not have an influence on my 12th cross where I was there in the first place. If at all we have to consider all those interrelationships, then the things are going to become really more complicated, and actually it is not much necessary to consider all of them unless they are very important. Because me going to 13th cross or 11th cross from 12th cross is having a larger probability, then from 13th to 14th me going as a larger probability, and from 11th me going to 10th is going to be a larger probability. From 12th I move on to 10th, I have to move through 11th only. So that way, now don't say that, sir, you should have a helicopter. Don't say that way. I am going through my bike only, imagine that way. Then from 12th I go to 10th, then I go to 9th. Okay, I should laugh for my own stupid jokes. Anyway, so this residual influence lasts only for a duration of one symbol. This we are specific to consider. Otherwise, instead of Pij, we should write Pijk if at all we consider more than a symbol. Or we should have to consider Pijkl, something like that, if at all we consider 2, 3, 4, 5. But it does not matter much there. Why? Because when we multiply more and more of the probabilities in the decimal fashion or in the fractional numbers, the effect is not going to be really too large. That way, here the residual influence is lasting only for a duration of one symbol. That is, the probability of occurrence of a symbol depends on the particular symbol in question and on the symbol immediately preceding it, with no dependency on the earlier states. This means that the transition probability to S3 depends on S2, but not on how the system got into S2. Now, the transition probability to state 3 depends on state S2, but we are not worried about on how the system got into S2. If we have to consider, then the computation becomes still more lengthier. So this is where we deal with the information sources using Markov process. In the next classes, we will work out some more examples. For this particular class, I will stop now. I am going to put the attendance link in the Google class. See you in the next class. Until then, take care and bye-bye.